Download this code from codegive.com, link in the description below. Certainly. Running executables in Linux involves several key components of the Linux kernel and the system's architecture. Below, I'll provide an overview of how Linux executes a program, along with a simple code example to illustrate the concepts. Overview of how Linux executes an executable. 1. User space versus kernel space. Linux operates in two main modes, user space and kernel space. User space is where user applications run, while kernel space is where the core of the operating system runs. 2. Executable format. Linux typically uses the executable and linkable format, ELF, for executables. When you run a command, the kernel needs to find and load this ELF file. 3. System calls. When a user wants to execute a program, they usually do this through a shell. The shell uses system calls to request the kernel to load and run the executable. 4. Forking and executing. The typical process for running an executable involves two main system calls. Fork. This creates a new process by duplicating the calling process, the shell. Exec. This replaces the current process image with a new process image, the executable. 5. Loading the executable. The kernel loads the executable into memory, sets up the stack, initializes the process environment, and then transfers control to the entry point of the executable. 6. Process management. The kernel manages the execution of processes, including scheduling, memory allocation, and handling of system resources. Step-by-step process of executing an executable. 1. User invokes a command, example.my_program. 2. Shell calls fork. A new process, child, is created. 3. Child process calls exec. The child process replaces its memory space with the executable's memory space. 4. Kernel loads the ELF file. The kernel reads the ELF header, loads the program segments into memory, and sets up stack and heap. 5. Control is transferred to the executable. The kernel starts executing the code from the entry point defined in the ELF file. Code example. Let's create a simple C program, my_program.c, to demonstrate this process. C. Include stdio.h. Include stlib.h. Int main. Printf, hello, world. This is my_program\n. Return 0. Compilation and execution. 1. Save the code in a file named my_program.c. 2. Compile the program using gcc. sh. gcc o my_program.c. 3. Run the program. sh. /my_program. What happens behind the scenes? 1. When you run ./my_program, the shell uses fork to create a new process. The new child process will then call exec to execute my_program. 2. The kernel reads the ELF file's header to determine how to load it, allocates memory for the executable and sets up the environment, transfers control to the entry point of my_program, which begins execution. Conclusion. The process of running an executable in Linux involves a detailed interplay between the user space, kernel space, system calls, and the ELF format. Understanding these components provides insight into how operating systems manage processes and system resources. If you want to delve deeper, consider exploring topics such as process scheduling, memory management, and the specifics of the ELF file format. Certainly. Understanding how the Linux kernel runs executables involves several components of the operating system, including the file system, process management, and the execution model. Let's break it down step by step. Overview of executable files in Linux. In Linux, executables are typically binary files that contain machine code, which the CPU can execute directly. Common executable formats in Linux include ELF, executable and linkable format. When you run an executable, the kernel is responsible for loading this file into memory and starting its execution. Steps to run an executable. 1. Command invocation. When you type a command in a shell, like bash, the shell interprets the command and determines if it's a built-in command, a script, or an executable binary. 2. Path resolution. If it's an executable, the shell checks the directories listed in the path environment variable to locate the executable file. 3. Loading the executable. The kernel is invoked to load the executable file into memory. The kernel reads the file header to determine the architecture and load the appropriate segments into memory. 4. Creating a process. The kernel creates a new process using the fork system call, which creates a copy of the current process. 5. Executing the program. The kernel uses the executable system call to replace the current process's memory space with the new executable's code and data. 6. Running the program. The CPU starts executing the instructions of the new program. Example, running a simple C program. Let's go through a simple example of creating and running a C program that prints Hello, World. Step 1, write a C program. Create a file named hello.c. C. Include sto.h. Int main. Printf, hello, world, \n. Return 0. Step 2, compile the C program. Use GCC to compile the C program into an executable. Bash. GCC oh hello.c. This command creates an executable file named hello. Step 3, running the executable. Now, let's run the compiled executable. Bash. /hello. What happens under the hood? 1. Shell command execution. When you run ./hello, the shell looks for hello in the current directory, preceded by /. 2. Kernel invocation. The shell uses system calls to request the kernel to execute the program. The executable system call is invoked with the path of the executable and its arguments. 3. Loading the executable. The kernel reads the ELF header of the hello executable to determine its entry point and load necessary segments, code, data, etc., into memory. 4. Process creation. The kernel creates a new process using fork, which duplicates the current process. The new process's memory space is then replaced with that of the hello executable using executable. 5. Execution. The CPU begins executing the machine code found at the entry point specified in the ELF header. The program executes and prints hello, world, to the standard output. Conclusion. The Linux kernel plays a crucial role in running executables. It manages the loading of executables, process creation, and execution, allowing users to run applications seamlessly. Understanding this process is fundamental for anyone looking to delve deeper into operating system design and development.